All right, so if you're looking for F sharp, you're in the right place. I'm Dave Fancher. Start off with this quote from Alan Perlis. Some of you may be familiar with it. A language that does not affect the way you think about programming is not worth knowing. He wrote that back in 1982, and I think that, excuse me, I think that it's still just as applicable today as it was back when he wrote that. So a little bit about me, Dave Fancher. You can find my blog, my Twitter feed, email me. As I just said, I wrote a book, and I'm an MVP for Microsoft F sharp. So my background, I've been developing software for a few years. Used that one, mostly C# and .NET, but active server pages way back when. Don't ask me to remember any of it. I don't want to bring back those days. And did some classic VB and everything, but C# has been the majority of what I've been working on through my career. Most important for tonight, I love F sharp. It says it on the screen, it says it on my shirt, and hashtag F sharp. So the question I get a lot is, why F sharp? And putting my thoughts together a while ago, it really came down to a lot of people are like, why did you set out this path? Why not Scala? Why not Haskell? Why not Erlang? And the problem I had with that question is that it assumed that I had an intention to learn a functional language. And that's not what happened. What really happened is that I outgrew C# and F sharp more closely matched the way I think. So a few years ago, I discovered this thing called LINQ. And you may have heard it referred to as a functional drug, but it's based on functional principles. So, the query syntax that everyone is familiar with is really just syntactic sugar that the compiler translates into a chain of method calls, right? Well, when I was first learning LINQ, I learned the query syntax to start with, and then I was reading that was only added after some initial focus groups said, we don't understand this dot syntax thing. We don't understand delegation and lambda expressions. All this stuff is like magical voodoo stuff. We don't get it. Make it easy. So they wrote this SQL-like language. But as I was looking at it, I'm like, how is this complicated? This is a function, this is a method, and it just data flow. It's like things aren't changing. You're dealing with immutable data. You're not introducing side effects. And so through the process of learning LINQ, I learned about functional principles like functional purity and referential transparency and higher order functions. And again, those things matched the way I think. So the other thing that kind of led me to functional was JavaScript. If you're treating JavaScript as an object-oriented language, as we've all been kind of programmed to do, you're doing it wrong. JavaScript is based in objects, but at its core, it's a functional language. And what is an object in JavaScript? It's a dictionary. So all of your functions are operating against that dictionary. And it's a semi-dynamic language, but it's really a dictionary. So a lot of its most powerful features, now some of the ways that people work with encapsulation, all of that stuff is done within the context of a function. It has function level scoping. So the function is actually the most critical thing to understand in JavaScript. Now you don't get things like default immutability, that's kind of a programmer discipline thing, but the principles still generally apply. So I started applying these functional principles in my code. My C# code was starting to have things like immutability through read-only backing variables. Yes, you can do things with private setters, but you still ultimately have a mutable object. Something inside of your method or inside of that class can change that data. And so I didn't like that, and I said, let's make it immutable altogether with read-only. I started finding myself using more delegation. When Microsoft added the generic overloads of action and func, those were great because I didn't have to write my own delegate classes anymore. I could just use those, and suddenly problems that were difficult to solve or required a lot of duplication just kind of vanished because I was able to pass these functions around as as first-class citizens of the language. And again, going back to kind of the immutable thing was was coding without side effects. So I didn't have to worry because I knew that my classes were fully immutable. If I passed something by reference into a method, I didn't have to worry about it changing on me. If you're dealing with mutable data, and there's a chance that that data can change within the context of a method call, the only valid answer for what does this method do is, I don't know. I think it does something, but you don't really know if that's going to change out from under you. So, C# was getting frustrating. It's a very verbose language. We spend a lot of time telling the compiler the same thing. You know, if you go all the way like I did with writing read-only backing fields, and you want to, since you have to set those through the constructor, you're telling the compiler 3-4 times what type something is, right? If one of our guiding principles now is don't repeat yourself within this interest, how can you follow that if the compiler itself makes you repeat yourself? I kind of alluded to fragility with the fact that anything can change at pretty much any time. And there's a lot of ceremony in writing C# code. You're setting up classes, you're setting up constructors, you're setting up backing fields. You have all sorts of plumbing code, the curly braces to denote code blocks. I've come to start calling them training wheels. Because you have this curly brace, and if you turn it like a tricycle or something on the side, it kind of looks like a curly brace. So one day, I'm mowing the lawn, and the podcast selection for the day is Hansel Minutes number 311 with Philip Chelford and Richard Minerich. And they're talking about this thing called F#, and it's a functional language built on top of the .NET framework, so a new CLR language. And I said, this is interesting, I need to know more. And so what is it? The exact marketing definition from when it first came out, according to Microsoft, F# is a succinct, expressive, and efficient functional and object-oriented language for Microsoft.NET that helps you write simple code and solve complex problems. Very, very marketing language, but it doesn't tell the whole picture. Since that was written, it's been brought into Xamarin, it's been ported to Mono, it's available across platforms. Originally developed as a CLR language from Microsoft Research. And if anybody's familiar with the name Don Syme, he's the inventor of the language, so to speak. He was heavily involved in the creation of .NET generics. So that was a pretty popular feature. It's incredibly powerful inside of F# too. It actually can do more. I don't really get into that today. But as it started, it's a derivative of ML, more specifically OCaml. Early versions of F# really strive to maintain some syntactic compatibility with ML, and there are a lot of compiler flags that exist even today that are for that, but they're not really used as much. The languages have kind of diverged a bit, especially recently, but that's where it got its start. And it's a multi-paradigm language. It has some imperative concepts. As a CLR language, it's object-oriented, and most importantly, it's a functional language. It's a first-class citizen of Visual Studio since version 2010. They released it as a plugin in 2008, and now it's under an Apache 2.0 license, and just recently they've started accepting pull requests to the public version of the language. So Microsoft has really embraced open source on that front as well. Every major platform, through Mono and now with Xamarin, it's easier to write F# for just about anywhere you want. It has a lot of community support. Just go and hashtag F# if you're writing something. Don Syme will probably retweet it. If he doesn't, Phil Chelford or Tomas Petracek probably will. And it's managed by the F# Software Foundation. So they control the GitHub repo, they manage and identify where user groups and everything are. So it's very open, very welcoming community. Why should anybody care though? People familiar with Tyobe? Criticize it all you want, but the popularity index showed an increase of 25 spots in popularity over the last year. This was actually a bit down, just a hair from the previous month, but this is May's index. I looked for a June index and they don't have one up yet, but this is kind of where it has, oh, there it is. That's kind of where it's been. So you can see in August 2011 it spiked. I don't really know what happened there, and then it kind of dwindled again. But since March of 2013, it's really taken off. And if you just follow the hashtag F# on Twitter, it's streaming. It's constant. You get a constant refresh on that all day long. People there's a lot of buzz about the language. So it's something that, you know, it's the fact that it's been a first-class citizen of Visual Studio for 3 releases now. It's not going anywhere, at least anytime soon. And it's a different way of writing code. So most importantly with F# is that it's a functional first language. What that means is it favors functional programming over other styles. You still have those if you want them. So if you have a particular problem domain that makes more sense to use object orientation, you can do that. If you're working on bringing in a new framework, most of your code's in F#, you can still implement interfaces. You can still derive from base classes. All of that is possible, but it just wants you to favor the functional programming, and the constructs and the syntax kind of guide you into that. By following the functional principles first, you will ultimately find yourself writing better code. You'll find yourself writing less code. And one of the things about functional programming is just the very nature of it. If it compiles, it's probably right, because you don't have to worry about these things changing. The compiler, you know, is kind of constantly referred to as your first unit test. Well, this one's even better, because you know that based on the flow of data, because the functions are deterministic, you know that if you're getting, it's compiling, you know that you're going to get a particular answer for any given input. It will be a particular output. So your programs are likely going to be more correct right out of the gate. Say for design principles. One of the things, if you go back to that original tagline, simple code to solve complex problems, it has a very terse syntax. So what that means, very few keywords. You think about C#. You have a keyword for interface, you have a keyword for class, you have a keyword for abstract, you have all of these different names for types, you have enums, you have all of these different types. In F#, you have one keyword, type. And then, if you want to control certain aspects of the way that the compiler handles that, so if you wanted to do an abstract base class, for instance, you would decorate that type definition with a particular attribute, and then the compiler will generate the appropriate intermediate language to make that an abstract base class. Limited punctuation, again, we go back to the curly braces. You don't have those. You're using white space to denote code blocks. So one of the things that the language designer said early on is that we're not going to enter into the tabs versus spaces debate. Everything is going to be spaced, because a tab can be an arbitrary number of characters. We want to make sure that you have an consistent level of indentation. So by making it a space as required hard rule from the compiler, you get that naturally. Strong type inference. So when we get into the code samples, this bit here is a bit bullet heavy, but when we get into the code samples, you're going to see something that's conspicuously missing from most of them, and that's types. Because the compiler, you think about C#, you have the var keyword, which goes into type inference, but it doesn't get you all the way there. You still have to tell the compiler for backing variables, you still have to tell it for properties, still have to tell it for arguments. A lot of times you don't have to do that in F#. It just knows, oh, there's a 0, that's probably an int. That's a string, okay, that's going to be a string everywhere. So it knows as you're passing things around, and it's able to infer what that actually is. So it looks like a dynamic language, but it really is a strongly typed language. And there are implicit return values because of the nature of the language, and we'll see as we get into this a bit, that you don't have to explicitly say, I'm going to return this value. the compiler knows, based on the way that it executes and the way that it evaluates everything, that the last expression evaluated is going to be your return value. And that's because of top-down evaluation. So these projects are organized a bit differently than you would expect in a C# or a VB project. Mainly, file order is significant. Also, declaration order is significant. So you can't access anything that was defined below. If you think about C# and VB classes, everything is, you can, as long as it's in scope, you can access it, right? So you can put your methods in any particular order, and you can put things in that don't make sense. You can get your private methods and public methods all scattered around. You can still scatter things like that in F# a bit, but as long as it's defined before, so you're never going to have to worry about it's going to be down below. Part of that says, oh, well, you have a mutually recursive definition, so that is prevented by F# because without using some specific syntax. So you don't end up in a spot where you end up with circular references that you don't want to, and so in order to do that, you have to be explicit about it. And we already talked about that. F# does have the concept of a namespace, just like every other CLR language. It's the same thing, same organizational concept. But what it also has is a module. Modules are pretty much the key organizational construct within an F# program. And to think of them in C# terms would be, it's a static class. So F# doesn't have static classes per se, it has modules. And inside of the module, you can open those, you can define functions, you can define additional types, and then you can open a module, import a module like you would a namespace, and then all of those definitions are available wherever that's open. F# is an expression-based language, so everything returns a value, and it uses eager evaluation. So that's not really a change from what traditional .NET programmers are used to, but because everything is an expression, even familiar constructs like conditionals, if, else, and try-catch blocks, they return a value. So if you want to get some value out, you don't have to deal with okay, well, I'm going to define my variable here, and then I'm going to execute this, and I'm going to have this mutable state, set that value that I just set, or, oh, I forgot to set that, now it's undefined or null reference exception. That entire class of problems is easily avoided. Finally, immutable by default. So we talked about the work you have to go through in C# to avoid mutability. Instead of having to go through the work to make things immutable in F#, you have to go through some hoops to make things mutable instead. So there are specific syntactic changes that you have to make to say, I have this value and I want to be able to change it. That serves as a warning to anybody reading the code. Hey, there be dragons here, this thing might change. It's not necessarily thread safe. You get that added protection just by reading through the code. It makes it easier to reason about your code because you know that if nothing's going to change, that it's going to be the same at the end of the function as it was at the beginning of the function. So here we have our first code sample. One more slide. So there are three types of bindings, and we refer to what C#, VB, a lot of your traditional .NET languages will refer to as variables. F# doesn't really have the concept of a variable. It has bindings. So you have the most common one is a let binding, and that's usually just it's like an assignment. Then you have use bindings, which are the equivalent of a using in C#, so that it'll automatically dispose of it. But it's nicer because you don't have to put it in a block. It's scoped to the function, and then when the function, whatever that function exits, it will dispose there instead. And then there are do bindings, which are used in certain limited circumstances, initializing modules, kind of like a static constructor, that type of thing. So here we have our first code sample. Let X get 42 and let name get Dave. Notice there's no type annotations there. It's just let. It looks kind of like JavaScript, but it's not because it's strongly typed. So we have the 42 and we have the string. If we wanted to change those with the assignment operator, as shown, where's my question? There we go. That's not showing up. That's great. So this is the assignment operator here, and it's saying that the IntelliSense is saying this is not mutable. In order to make it mutable, we need to change our definition to be let mutable name gets Dave, and then the next one we use that and the compiler no longer complains. Most of the time, if you're doing this, you're probably doing something wrong. There's few circumstances where you would want to make changes to that. That's a temporary holding area, but by doing it this way, you're keeping that mutability contained, and it's not. You should strive to keep that isolated as much as possible. The other way to get some mutability is through what's called a reference cell. So in this case, the definition is let name get ref Dave. This is doing is it's creating a concrete type called a reference cell. It's a reference of ref of t. So that concrete type is wrapping a mutable value, and then you can use the reference cell assignment operator :equals to set it, and then the following line there's the bang name. That is the dereferencing, so it'll pull that value out. So there's no additional functions or anything else on that. It's just built into the language. You need to use these whenever you're dealing with a function from another library that accepts things by reference. You can't use a mutable value. You can't use a mutable binding when you're using closures either. So if you get used to delegation, I think it was a post from Eric Lippert a few years ago who talked about all of the hoops that they had to go through to get the C# compiler to actually work with mutable values as opposed to going through a reference cell like this. For use bindings, I've actually got two examples in here. The first is the built-in F# using function, and the second here is the use binding. So the using function, just to show that it returns a value, is in line with our let binding. So that is much closer to what the using block in C# is, but it returns the value. It takes the iDisposable, and then that function that it's accepting as its second argument, where fun stream, we have the inline binding for use, and so when that function finishes and exits scope, that reader will be disposed. So we've got all that nested up there, nested in there. There's no additional blocks. You need to use a using function when you want to control a little bit more of the scope, or if you're working inside of a module, and it's a top-level definition, because the module, being a static class, doesn't ever get disposed of, so it never goes out of scope, so it never has a chance to dispose of that value. So that's where the using comes in.
So the code built before would return a string, right?
Right, yeah, because we're going to get the string from read to end, so XML is just going to be an XML string. And the IntelliSense, if you were to hover over XML, it would tell you this is a string. So getting into a little bit more of the type system, all of the CLR types are available to you. So everything you're familiar with, int32, string, double, all of those. The more complicated things, time spans, anything else from other libraries. So you can reference a C# assembly or a VB assembly in an F# project and use it just as you normally would. You get enumerations. I point out enumerations because there's a specific syntax to them that you need. They differ a little bit. They're exactly the same construct as you'd be used to in C#, but you notice that each one has an explicit value assigned to it. Unlike C#, which automatically assigns those values, F# does not, because it has a very, very similar syntax to another construct, which we'll look at in a little bit. If you don't do this, the compiler will get confused and say, I don't know what this is, and it'll try to create the wrong type. But functions. Functions in F# work completely different than you'd be used to in C# and VB. So if you think about a delegate in the other languages, you have, what, 9 generic overloads of func, 9 generic overloads of action, something like that, and then we'll not even talk about predicate, or some of the other frameworks which have their own custom delegates, or if you want to create delegates with out parameters or ref parameters or any of those things, it's just a mess to deal with. F# has one type of function. Everything accepts one input, everything has exactly one output. There is no concept of a void function, there's no concept of a parameterless function. That means you can do a lot more things with it. It's easier to talk about the code, and it's easier to predict what the code is going to do and reason about it. So in order to enable that, F# has a type called unit. And this is saying there's no particular value here, it's safe to ignore this. If you return something that's not unit, the compiler will say, you're not using this. It'll give you a warning right off the bat and say you need to do something with this value, or send it to the ignore function to explicitly say you're not doing anything with it. If you're doing that, that's indicative of a side effect and should be avoided. So whenever you see, you're looking at F# code and you see an empty set of parens, that's unit. All right. So, ever work with tuples in C#? Yeah? Kind of sucks, doesn't it? You end up writing code that looks like this. Var point gets tuple dot create 10, 20, var x gets point item 1, var y point item 2. What is item 1, item 2? This doesn't mean anything to me. I have to look at it. Behind the scenes, this tuple, this is a factory method that's creating one of 9 different generic overloads of a tuple of t to the x. And they're all incompatible, and they all kind of suck to work with in C#. F# uses exactly the same type, but it does it a little bit differently. So now I have let point get 10, 20, or I have let x, y get point. So if I was to have a function that was returning a tuple, I can put in x, y, and it will parse those values out of that automatically. There's none of this item 1, item 2 nonsense. You also notice that the signature is int times int. That's indicative that it's a tuple. So it's a single value it's a single data item, well, a single data type with the 2 values. In this case, it's a pair. That's indicative of I think that was a Cartesian product is why they chose the asterisk. So it's a lot easier to work with tuples. And behind the scenes, it's the same type, but it abstracts most of that from you. Historically, the tuples were in the original F# core assembly, and then in .NET 4, they moved them from F# core into MS Core Libs. So now, if you're working with the older versions, there might be some conflict, but not really anymore. Now, Jesse can attest to the times I complain about out parameters on things. And this is why. So if you're looking at C#, think about your try parse methods that you use to avoid exceptions, right?
This is the worst.
It sucks. It absolutely sucks. I hate doing this every time I do it. Okay, I got my int, sum int, and then I'm going to go and try parse, and I got my string, and I've got to do this out, and so there's this mutable value that I've got to set here, and now, oh, I can use it here, but if I try to use it elsewhere, it doesn't work, and I'll probably get undefined, or depending on the type, null reference exception, or that. F# doesn't have the concept of an out parameter. It doesn't allow it at all. So what does it do? If it has to have this interop between the languages, what does it do? Simple. It wraps it up in a static class and gives you a tuple back. So now, try parse is int32.tryParse passing in just that single value, And now we can go into pattern matching. Oh, the return value is true, but the other value was the one that was parsed. And that's only accessible within the right side of that expression. So now you don't have to worry about things getting out of scope or being uninitialized because it'll always be there. And then that bottom one is kind of a catch-all, and it'll say, oh, it was something else, it's something other than true in my value, so unrecognized. For everything else, because those functions work so much differently, when you need to call into another library, which does have the parameters all applied, the arguments all applied at once, the F# doesn't handle that, so it uses the concept of a syntactic tuple. So behind the scenes, it's not really a tuple, it just looks like one in F#. As far as F# is concerned, as far as the compiler is concerned, it's behaving like a tuple. But that's so then you end up with a like string format call and just comma delimited list like you would if you were working with C# directly. All right. Another important type in F# is the record, and the record is a very lightweight syntax for simple objects. So think about the work you need to do. If you just have a simple data transfer object, you've got a series of properties, probably a constructor to accept it, maybe some backing variables. Think about all the code you need to write. So just say 3 properties. That's it in F#. So for defining an RGB color, 3 values, R, G, and B. This one you actually do have to include the type annotations. So I've identified these as int. If I want to create a new instance of this, it's not like the same. It's not like I'm going to say new RGB color. It has a special syntax for that, and it looks just like the definition. The compiler says, oh, you're setting a thing, we're inside these curly braces, and you've got an R and a G and a B, it must be RGB color. Now, you can get yourself into some trouble with this because it's looking for the most recent definition as far as the top-down evaluation goes. So if it finds another record type with the same definition, it'll say, oh, it must be this RGB color 2 instead. But you can more fully qualify one of the elements in there to be RGB color, and that'll work around that problem very easily. But, okay, it's a common thing that you want to copy these data transfer objects, right? So rather than having to go and use this syntax every time, or if I wanted to say, I could do, if I had a blue up there, I could say the R is 0, the G is 0, and the B is FF. Or I could do, in this case, black, red with, and now I'm going to just change the red value to 0 and get me a black. Very convenient syntax. Oh, and before I forget, the other nice thing, so even though this is only 3 lines of code, if you look at the code that's generated by the compiler, if you look at the MSIL for this, you'll see that there's a lot more in it. It does properties, it does a default constructor, but one of the really cool things that it does for you, because these are immutable by default, it can override equals and get hash code and give you structural equality. So you can take any 2 arbitrary records, as long as they have the same structure, and it will do the comparison against each individual field to see if they're correct, as opposed to doing object references and that type of equality check. You can make these mutable, but if I was to change like the R, I can make that a mutable R, and then you can change values. But again, you probably don't want to do that in most cases. So
do the type contain other functions?
You can. There is a syntax to add additional functions to this. I don't really get into it in this talk, but there's also ways to extend types. I don't remember how well record types extend, but there are ways to put additional methods on here. But most of the time, these are intended for use as just simple objects, and you're just passing the data around. Most of the time, you'll end up writing these things inside of a module, which will have the associated functions anyway. Oh, also, prior to F# 3.0, these were kind of limited in what you could do with them. They were kind of isolated into the F# sandbox. They didn't play well with the default serialization and any of that. In F# 3, they added the CLI mutable attribute, and what that does is it allows behind the scenes, it actually defines a setter for each of these properties and lets the default serialization work with them very nicely. Discriminated unions are a type that we don't have in C# and are probably one of the most powerful concepts in F#. So they are immutable, they get you structural equality, and this is the type that the compiler can get confused of if you're trying to do an enum and you forget the value. And they're incredibly versatile. What they are is they are a type that are constrained to a certain number of values. So if you think about an enumeration, what is it? An enumeration is really just a label on top of a number, right? It doesn't really constrain you into anything but an integral value. And you can pass in an integral value that's not really part of the enumeration, and it can still be treated as that enum. With a discriminated union, that's not the case. So when you define something like shape, we have a circle, a rectangle, and a triangle. You can write a function that accepts a shape, and it can be only one of those three types. So you can't pass in something else. If you want to extend it, you add another union case on here. What this is doing behind the scenes is it's generating an abstract base class and 3 nested classes. A simple one like this, I think I brought it up in ILSpy, and it was some obscene 100 numbers of lines of code to generate the code behind this. Because what we really have is 3 distinct types with associated data. So they can carry more than an enumeration can as well. And then we want to create an instance of a rectangle, let rect1, and we can use either a straight value syntax, or we can use the a name value pair. It looks like this is one of those places where it's a syntactic tuple. Behind the scenes, it looks like a tuple, but it's not. And the other thing we can do is use discriminated unions as simple hierarchies or trees. So very similar thing, but you notice that we have a recursive lookup here. So type markup, content element of string, and markup list. So that particular element can have nested markup elements. And the example below is just putting together a simple little HTML block. But you can then parse that, and we'll look at some pattern matching in a little bit to see how easy it is to extract the value and convert that to something else later. About a year ago, this was going around on Twitter. A guy asks, what can C# do that F# can't? So far, I've only found flags, enumerations, extension methods, and an object. Well, the flags enums thing doesn't apply anymore. It's that one you can do. And I'm not sure about the extension method on object, but Tomasz Petrocek, who's well known in the F# community, replies with null reference exception. I don't know, but I don't think more than a few hours passes before I hear somebody saying, hey, there's a null reference exception. And how much code do we have to write to deal with null? I was reading, I think it was in Clean Code, where it says, I've seen systems where every other line is a null check. Why do we have to write that all the time? Why should we? F# says you shouldn't have to. And it uses an opt-in approach to nullability. It doesn't, if it wasn't for interacting with other languages that allow null so readily, F# probably wouldn't even have the concept. You can't, without jumping through some hoops, even make null a valid value for something defined in F#. So what it uses is a concept of an option. And an option is a built-in discriminated union with 2 values, sum of t and none. And now you know, based on the signature of your method, if it's going to return an option of something, that hey, this might not return a value. Or it will have something and you can handle it appropriately. So it's a warning, and you don't need to spend all that extra time worrying about, well, is this thing going to return something or not, or handling. handling empty lists versus null lists. You just say, oh, I'm getting a list back, or I'm getting an option of lists back, and then you can handle that appropriately. And you can see right in that signature that in this particular method, my open file function is it accepts a string and returns a file stream of option. All right. Anybody recognize any of these? The first on the ship is the Vasa warship from 1628. When it was discovered, it's known because it sank less than a mile into its inaugural journey. Why? Because its construction was asymmetrical. They had two teams working on it, and from the evidence uncovered, there were two different measurement units involved. There were Swedish feet versus Amsterdam feet. So one side was, I think, 11 inches thick, and the other was 9 inches thick, and so it ended up killing 30-some people and lost. It was considered, when it was being built, to be the most advanced warship of its kind. The one on the opposite side is the Gimli glider. It was the first Air Canada flight after they changed the measurement units from imperial to metric, and the crew followed the instructions as written in the instruction manual, but ended up with only having half the amount of fuel to get where they needed to go. They ran out of fuel and had to make an emergency glider landing, unpowered, into airbase. And the one in the middle is the Mars Climate Orbiter, which is a little bit more recent than the others, but that was because two teams working on it were confused, and one of them was using newtons, and the other was using imperial units.
Joules.
Yep, and so it kind of crashed and sent a few $1 billion with it. So, two of these were more analog, and the third one was completely computerized. And you can argue that the lander should have been, could have been caught in unit testing, but I would argue that if the language itself would actually enforce units of measure, that wouldn't have happened at all, because you can write a function such that, oh, we want inches, or we want feet, or we want centimeters, and if the language enforces that as part of the type system, you don't run into that problem. F# is one of the first languages that does that. And this is one of the things that sold me on the language early on. I was working on a program at the time that was using, I was dealing with inches and DPI and pixels, and a couple of times, oh, which does this take? Well, outside of naming conventions in most languages, you can't really enforce it. Now, it's purely up to programmer discipline and documentation and everything else. Let the language do it. Computers are good at this type of thing. So the way that F# does it is it uses a generic-like syntax. So first, we have two types defined, type pounds and type kilograms, and they're decorated with a measure attribute. And then we have two values, imperial and metric, and we can see that we're using pounds and kilograms on there. And I have a live demo for this. Now, let's jump over to Visual Studio. And I can't see that from here, so I'm assuming nobody else can either. Yeah, you can. I can't see my mouse either, so. Okay, let's increase the size a bit. Okay, just a moment. I've lost my cursor. That better? Okay. So in this particular example, still can't see anything. Okay. Okay, so in this example, this is not using unit safe code. So, we're not using unit safe code. So we have our Fahrenheit to Celsius conversion accepting a temperature, and a Celsius to Fahrenheit conversion also accepting a temperature, but we don't know anything about that. Versus this code, which we've defined our types, and our Fahrenheit to Celsius now accepts an annotated temp, which is a float of F, and it returns a float of C. So we know at the language level what we're expecting, and the compiler will enforce that. So if we look at the calls down at the bottom, if I'm changing this, if I forget to include the unit, for instance, now the compiler is yelling about it. I've got squigglies under the 212, and it's telling me that it's expecting a different type. Or if I use the wrong one, we get the same squigglies telling me it's a different type. So the compiler handles that. There are frameworks and stuff that can do this in other languages, but the problem with them is that they're frameworks, so they don't now. And they add additional complexity. This is just part of the type system. So with units of measure, it is an F-sharp language feature, so it is kind of constrained into the F-sharp sandbox. They get erased at runtime. The types still exist in the compiled code, but they're erased off of, the decorations are erased off of the values. So going across to C#, it would just be a unitless float in that case. And anything coming in from C# or VB will be without units too. But as long as you're within that F# sandbox, you get that full added safety. I'm not going to spend a whole lot of time on collections. I just want to give a quick look at a few things here. Sequences, of course, your IEnumerable of T. Arrays are your built-in arrays. Lists are not your normal lists. Lists are a separate construct we'll look at in a little bit in detail in a moment. And then you have maps and sets on top of that. With all of those collection types, you have collection modules. And the collection modules provide additional functions for manipulating those particular sequences or collections. So sequence has a sequence module, list has a list module, array has an array module, and so on. And a lot of the things in there are link-like operations. So I end up falling into talking about maps and reduces and filters, whereas people that are more familiar with link would be talking about selects and aggregate and where. They're a lot of the same thing, but then there's additional things on there. There's most of them correspond to things that are implemented in link. So F# lists, these are the important ones. They're used all the time. They are not your list of T. They are F# list of T. Implemented completely different behind the scenes. So if you look at a list of T, what is it? It's a wrapper around an array, right? And when you're adding things to it, what is it doing? Oh, it's looking, do I have enough room in this array? Yes, I do. Set the appropriate element. If not, okay, create a new array, move everything over, and now I've got that. It's aliased in F# to actually have an appropriate name called resize array. F# list of T is based on a linked list. It's immutable. It has the bracket syntax, has a list module. It's a cons operator and a concatenation operator. So the cons operator lets you prepend items. It's putting things at the very beginning. And the concatenation operator is going to join two lists. And it's a very quick operation because you're just changing the pointer or inserting a new pointer within the linked list as opposed to recreating the whole list all the time. What that allows is some additional functionality that's really effective in functional programming because it follows a head and tail model. So instead of just iterating over everything, you can get the first element and everything else, which is really useful in recursive situations. So you can see how the list composition works with the cons operator and the concatenate operator. So you end up with two lists. Very, very easy syntax. You also see I mixed in the range operator, the double dots, kind of Ruby-esque there. That one's very convenient. That's a lot more powerful than enumerable.range, because it lets you do more than just int. Right. Oh, overview of OO in F# before we get to the really good stuff. So I mentioned earlier it's really useful for language interop. If you want to bring in any of any library you're familiar with, probably be tying into it. And it can do, you can create robust frameworks in F# as though it were C#, and they can hold their own against anything created in C#. You'd probably just be writing less code. So you're going to see something that should look very familiar in a moment. The syntax here, type RGB color. So this is a full-blown class with a primary constructor and 3 methods. It looks a whole lot like C#6, doesn't it? This is where they got it from. If you want to know where C# is going to be in the future, look at F# 2 years ago. C# won't quite get where F# is because it doesn't have some of the stuff we'll talk about in a minute, and it probably won't ever get it. But this is what you need to do. That same thing, that record type that I showed earlier, this is the same structure, but this doesn't give us out of the box all of that structural equality that we saw before. Interfaces, again, you can kind of see a pattern here. I've used type for RGB color, type for iColor. It's the same keyword for defining the type, but because we only have abstract members on here, the compiler says, oh, only abstract members? It's an interface. So it'll by default do that. If you wanted it to be an abstract class, you would put the abstract class attribute on there and it would change the way it compiled. To implement that interface, well, we've got our RGB color class that we saw before, and we said interface iColor with, and now we've defined member C to hex, and so C is going to refer to this object. It's like this, but you get to specify what it is. You're not constrained to using the word this. And that lets you kind of segregate your interfaces a little bit, so you can say, oh, I'm using it this way, and the other thing, or this other interface is using this identifier, so it just gives you a little bit different cue as to what you're working with. With interface implementation, it's important to note that all interface implementations in F# are explicit. So if you think about C#, you have implicit and explicit, where implicit says you just toss the members on there and you can treat the type as that interface, versus the explicit one where you define it, you just basically you have your return type and then the interface type dot member, and then you can only access that member if you're treating that object as that interface through the polymorphic behaviors. All interface implementations are like that in F#. The reason is because if you're converting or something, it's kind of a side effect. You're working with a different type, so you need to be explicit and do an explicit cast to do that if you want to implement you want to use the interface members. Inheritance and virtual members. So we'll start a little bit at the bottom here. So this second class ARGB color, we use the inherit RGB color, and we're calling that base constructor. So RGB color has RG and B int as its primary constructor. We're calling that, passing in the values that were passed down. And then we're overriding the 2 hex. Now, if you notice the definition up above, you see that there's 2 lines for 2 hex. There's an abstract and a default. This more closely resembles the way that the CLR handles abstract members. So what is it really doing? When you define a virtual member in C#, it first needs to allocate something in the virtual method lookup table, right? And then it has to have an implementation of that. And that's what the default is doing. So abstract is doing the allocation in the table, and then the default is saying, here's that default implementation. So it much more closely resembles what's really going on behind the scenes. This is another one of my favorite features. I use this one all the time. The object expression. So think of an object expression as a lambda expression for types. So where a lambda expression lets you use a function in line, right? You don't have to go through the ceremony of creating a formal one. Well, in this case, I have a let create RGB color method or function, and then I've got this nice curly brace syntax around new iColor with. Wait a minute, iColor, that's an interface. I can't create a new one. Yes, you can. As long as you define a member or an implementation for all of the interface methods and members, then you're fine. And so that's what this is doing. Saying member x to hex, and then we're using a little syntactic sugar to print out the hex values for the RGB. And it's really nice. I use this thing quite frequently. It's great. And then you can see in the second line, the final line, in parents, create RGB color 25500 to hex. So we get the compiler creates the type for you behind the scenes. You can do this with interfaces. You can do it with base classes. Now we're into the really good stuff. Familiar with Bob Martin? He said in a blog post about a year ago, functional programming is programming without assignment statements. You're working with bindings. You're working with immutable values. So F#, as far as functional purity goes, functional purity being whether or not things can change. F# is an impure language. Languages like Haskell are pure languages. So mutability and side effects are allowed, but granted, they're typically controlled. Oops, I forgot to set that right. All right. So functions as data. Of course, a functional language wouldn't be anything without functions as first-class citizens. So it makes it very easy to write higher-order functions, let-bound functions inside of your modules or inside of additional other functions. They just be nested, returning functions, and lambda expressions. So here, list, init, 10, and then a delegate to create to populate 10 items inside of that list. The real power of the functions, though, we go back to that whole structure of exactly one input, exactly one output, comes from currying. Named after the guy, Haskell Curry. He didn't invent it, he just popularized it. I can't remember the name of the guy who actually invented it. Arguments are applied individually. So when you see functions and it looks like they have multiple parameters, it's a syntactic trick. They don't. We'll see an example of that in a minute. Changes and currying changes the way you organize your functions. So consider this add function. This is what Brad was talking about a little bit before the meeting. We have let add take A and B, and it's just going to add the two numbers, right? What that's actually doing is it's creating a function that returns another function so that you can chain them. It really looks more like this. Let add A with a closure around A, returning a function that will invoke the operator with those arguments. Now, it takes a little while to get used to, but when you realize the power of it, you end up with this thing called partial application. Partial application is used everywhere. So we take that same definition, let add AB, and we want to create a new function called add5. I don't need to call add over and over. I just need to create a new line, let add5. The result of invoking that first function is a new function. So add5 has an implicit parameter. You can tell from the signature. It accepts an int, and it returns an int on our add5. The original add is int, arrow, int, arrow, int. So you can see these methods building up, which enables pipelining, which is the coolest thing, and which is probably the thing that these guys hear me complaining about the most. So convert Fahrenheit to Celsius function. I have a list of temperatures that I pipe into the average function, which the output of that is then piped into convert Fahrenheit to Celsius, which is then piped into a print statement. So that same list gets reduced through list average, The output of that is then sent to convert Fahrenheit to Celsius as the final parameter, which is then in turn sent to printfn as the final parameter. But here's another example of partial application, because printfn is a curried function that accepts a string format and arguments. Pipelining is a single-use feature. So it's something that's inline, and you have it in your code, and you can invoke your method that contains it over and over, but it's still just the same. But if you want to use that same chain over and over, you can do function composition with a double arrow operator. So convert Fahrenheit to Celsius, and then get average in Celsius is now going to be a function that accepts a float list and returns a float. So all of that just gets chained together, and your data just flows through the application. You're not changing any of it, you're just operating against it, creating new lists, calculating that, so your original value is staying intact, but it's just flowing through. You can see the execution just by reading the code. And just a brief bit of a recursion. So it's a preferred looping mechanism. It does have while loops, it does have for loops, but usually you're going to go with recursion. And the compiler optimizes for tail calls, so you don't have to worry about, provided you've written your function correctly, you don't have to worry as much about Stack Overflow exceptions. Pattern matching is like a switch statement, but not really. It looks like it, but it's not. So match r.next5 with 1, print 0, print 1, print 2, pretty much a switch statement. Except that's about the most simple case you can get. There are built-in patterns for null, so when you're getting something back from C#, you need to check for null, and that way you can contain it. Variable and wildcard patterns match everything. Literals like 0, 1, and 2, and so on. All of these things, you can combine these patterns to give you decomposition. So this is actually defining a function. The function keyword here is a syntactic shortcut for the match with that we saw there. This is implicitly accepting a tuple, and we're going to look for something at the origin, something at the x-axis, something at the y-axis, or just some random point. By matching like this, we are able, and because of the nature of the language, we're able to make more assumptions about the code, and we can say, in this case, oh, we're matching against tuples. We need to make sure that you match everything. We're not going to have a fall-through case. We're not going to have a... When you do that, your cases are said to be covering. And if I wasn't to include that bottom case, the compiler would throw a warning and say, you've missed something here. We can do the same thing with discriminated unions. We can say, oh, circle, rectangle, triangle. It can only be one of those. If I left out circle, the compiler would complain. If we're matching against integers, and you match 1, 2, 3, 4, 5, and you don't have a wildcard pattern at the end, it says, oh, you might not have handled 6. And if you go in and put in 6, it'll say, you might not have handled 7. So that's where the wildcard comes in. And if you say, you get that extra safety, and you can match against that. And again, as we saw earlier, that R or the W and H or L1, L2, L3, those are only available within the context of the expression on the right-hand side of the arrow. You can combine some of these. You can do guard clauses on these so that you can have the same basic pattern, but if you want to do like range checking, you can do that. You're not limited to integral type checking like you are with a switch statement. If the built-in patterns aren't enough, you can use active patterns, which allow you to specify custom things. It's called an active recognizer function. They are curried so that you can chain them a little bit differently. They have an implicit input parameter, a final parameter. You can parameterize them more. Unfortunately, active patterns are limited to 7 cases. I've not ever been able to find out why. It seems like in everything I've seen about it seems pretty arbitrary. But hope is not lost, because there are partial active patterns, which take a single case. They have to return either that case name or none. So it's an option of the active pattern or none, and all of that magic of doing the switch against some or none is handled for you by the compiler. Not restricted. I already talked about that. So I'm going to jump back to Visual Studio for a moment. So in this case, I'm just doing a little FizzBuzz sample. I'm sure we're all familiar with that one. And we have two active recognizers for fizz and buzz. On the right, you'll see that I just executed that. The window on the right is F# Interactive. That's the REPL that comes with F# that allows you to explore your problem space a little bit. Very, very useful. It's your best friend when you're working with F#. It's more than LinkPad because LinkPad is not a REPL. LinkPad is useful, but it doesn't retain that state for you. So now I've executed that. If I was to execute again,
I'm going to open let's move the center of the window over just a little bit so you can see the top of the first two lines.
yeah, let me bring that over so you can actually see what I'm doing. I'm going to make it in the bottom. Better?
Mm-hmm. Yeah.
All right, so just simple functions up on the top. And now I've got a new function called FizzBuzz, and it's matched against fizz and buzz or buzz or anything else. Define that, and you can see our int, so that it automatically generated the name for that implicit parameter on that function. And now I can execute this sequence comprehension that pipes to the map on the sequence module and then pipes the result of that mapping into the iterator. And the bottom, we can see all of our fizz and buzz and all that stuff. So pattern matching is incredibly powerful. I'll be jumping back to Visual Studio here in a minute. Data access is a very important point in F#. It has query expressions which are LINQ for F#. They're really nice, but syntactically they're not really all that interesting. What gets really cool though is type providers. Type providers were introduced in version 3, and think about the work, before I go into the demo, think about the work you have to do using an entity framework or an nhibernate for data access. You've got to create your mappings. I mean, you use things like Fluent nhibernate to help with that, getting away from the XML and whatnot. But there's still a lot of work. You've got to maintain those mappings files and everything. It's just a lot of work. Type providers work to get around that, but they're a lot more flexible in what they can do. So I'm going to jump back to Visual Studio, and this will be the first time I've run this against F# Interactive since earlier. Hopefully my network connection hasn't dropped. We open the file here, and I'll switch Visual Studio back. All right. Cursor. The first two lines, this is for F# Interactive, are telling F# Interactive to open these two assemblies. So we'll run those, and you'll see that it's referenced both of those. I'm going to open the namespace, Microsoft F# data type providers. So that's just doing my import from those. And now this next line is defining a new type of OData service, and you'll notice that URL is pointing to an OData service. It's a publicly accessible one from odata.org for their Northwind demo. I'll run that. This takes a moment because it has to go download some stuff and create some types behind the scenes. And we look, it created a type called Northwind. It's a class with a static member of getDataContext. And it has an overload, and it's got some nested types in there. Now we'll execute the next line, which is going to get us a data context. And from there, we'll say, let's go and query that. So you see the query expression built in right here. We're just doing you see how it's very much like LINQ. Query for I in service.invoices. Where did that service.invoices come? I didn't write that code. All I did was create an instance of service from get data context. I created this Northwind type. I didn't write any of that code. The type provider, through the compiler service, ran out to that OData service, read the schema, and generated the types for me.
Would you have gotten the .invoices through IntelliSense?
Yes.
Wow.
Yeah, because it is a type. If I can find my cursor, I can actually bring that up. I can go Control J there, and it's hard to see there, but these are all the types it generated for me.
Very cool.
But it's only after you actually did the
Once you connect, once you connect to it, but the first time you try to use a type provider, Visual Studio is going to say, this is a potential security problem, you're going to go out to the internet, yeah, that might be bad. So it asks you to confirm that you want to do that, and then there's a thing in the F# options dialog to control which ones have it. So even once you bring that in, it'll go and query. It's not a matter of just running it. The reason you didn't really see it before is because I'm running this as a script file. Is that if this was in the code, it would have generated in like a library project that would have generated that for me behind the scenes. And now, this is just like LINQ using deferred execution. So now if I take my invoices and pipe it to my iteration, I just took 5 from that, so it's not a very big data set. I run that, and I broke something.
I don't think you executed
I didn't
that.
know invoices, did I?
Yeah.
Yeah. There we go. And that went out to the OData service for me, and I didn't have to do anything. One of the things that makes type providers even more cool, though, is that they're not limited to database work or OData services necessarily. So there are built-in type providers for OData, for SQL, for I think DBML files, and a whole bunch of others. But then there's other community projects like F#.data and F#X and a few others that have additional providers built in. There's even one of the examples I talk about in the book is a regex provider. So if you're thinking about the regex with named captures, rather than trying to go through and deal with matches and everything, the regex type provider will parse your regular expression, find the captures, and then when you match it, it will give you back an object that has those names as properties. So it's really slick. There's just a whole slew of them out there. There's one for config files. There's one for, I think at one point there was one for the file system, and there's just all sorts of stuff. There's all sorts of power. There's type providers for communicating across languages. So there's a type provider that's been in the works lately for people working in data science type things, working with types from the R language. There's a type provider that's in the works for Python. So going across all of those domains, you can have things communicating that way. They're just incredibly powerful. People are finding all sorts of things to do with them, and it's really cool to watch. I have yet to write one, but it's something I just would like to do sometimes. It's really kind of cumbersome, but it's cool. All right, there we go. Next, as a functional language with default immutability, F# lends itself very, very well to something that's growing in importance, and that's asynchronous and parallel programming. So if you don't have things changing on you, you don't have to lock as much, right? At least that's the idea. Makes it a lot easier to write that. F# does something different. F# has had this for a while. It predates async and await in C# by quite some time. And they did something with an asynchronous workflow. So you can use the full task parallel library, but that's not really part of F#. The asynchronous workflows can tie into the TPL, excuse me, but they aren't necessarily part of F#. Asynchronous workflows, though, they're like async and await, but they work using lightweight callbacks and continuations. So you're still chaining things together, but it has a very, very cool syntax. And one of the key uses for it is agent-based programming like you'd see in Erlang. That's where most of this came from. It uses an in-memory queuing mechanism that they called mailbox processor of T. I think that came from Erlang too, but everybody uses a type alias for agent of T, and it makes it a little bit more readable. And I think I have an example of this. Yeah. So, sorry, Ray.
Oh, no worries.
This is the demo heavy part. Because some of these things are just so much cooler to see than to actually just hear about. I'm going to reset my F# interactive down here, and then I will switch that back over. All right. First thing we need to do here is define our we'll just alias mailbox processor like everybody does. And then we have a discriminated union that we're defining our operations, and each of these basic mathematical operations, add, subtract, they all accept a float. And then we have a clear and a current of async reply channel of float. So that allows us to do some bidirectional communication with our agents and and query the current value. So let me invoke that. Right, and it created that type. Now we have a long function called calcagent, which calls agent.start, and it accepts a function with a inbox parameter, and it's got a nested recursive loop inside of it. And all that's going to do is just continually call inbox.receive, which will just sit there and wait for something to enter that queue. And when it gets something, it will do a pattern match against that discriminated union type, pulling out the value, and creating, doing the appropriate calculation, and then recursively calling loop and keep track of that state through the recursive call. Try my cursor. Run that. And it created calcagent mailbox processor. So that thing's running now. It's just sitting there spinning. It's very quiet. If we look at my process, it's not going to really show anything here, but yeah, there's not a whole lot going on here. I've got more CPU stuff going from the Bluetooth connection than for my phone than anything else. But it's just sitting there spinning and waiting for some input on that agent. Create a list of 4 operations. And all I'm going to do is iterate over that list calling calcagent.post. And you'll see the return value of that was unit. Now let me call a post and reply. I got the result out of there. If I clear it, just picking that up, and we see that it's 0. So this is just going to sit there and run. And what's really nice is because each of these are very lightweight processes, you can use these to orchestrate communication across your system. Now, this is all in memory, but if you want to orchestrate some type of bus and have different handlers for different types of things, these can all communicate with each other, and it's very, very light on the system resources.
And there's a pretty neat package of guys written for doing remote agents and stuff. So if you want to spawn compute across a bunch of machines,
it's very, very good stuff. And the fact that it's all the fact that it's functional makes it even easier to write that type of programming. It just is, and we'll see. I didn't really go into the details on the asynchronous workflow or the query expression so much, but the way that those are constructed is the topic of this section here, which is extending the language. So F# has this concept called computation expression. Other languages refer to it as the monad, and it's really, really cool. I don't claim to know anything about monadic theory, but it's really cool with what it can do. So with computation expressions, like I said it here, it's the basis of several language features, namely sequence expressions, query expressions, and asynchronous workflows. They are built, complete language feature. A sequence expression is a bit of an anomaly in this because it doesn't work quite the same way. It's baked into the compiler directly as opposed to going through the same processes. But it's syntactically it's the same. It's considered to be a computation expression. Behind the scenes, with the exception of the sequence expression, they're based on a builder class. And within that class are a number of methods that need to follow a certain naming convention in order to work, but the compiler will take those expressions through a process called desugaring, just like the link query syntax, and convert it into a chain of method calls for you. So I'm going to jump back into code because this one's a lot easier to see through code. And I think the example is fun. Let's go open that one. Reset.
While Dave is doing that, one of the, and it may not be obvious if you don't use a sharp like I have and Dave has, whoever else here has, but the amazing thing is you'll see there a couple, but you almost never type types in your code. It's, if you're used to C#, or if you're a Mac person who's just discovered Swift or something, then you're familiar with local type inference where you can do var, and it can sort of figure out what's on the other side of your expression. But in F#, it's basically doing that for all of your code. It's looking at all of your code and trying to figure out, this calls that, that calls that, that calls that. What can we constrain it down to a particular type? And if it can't figure it out by looking at all the code, then you wouldn't be able to figure it out by looking at all the code either, other than by knowing context about the code. And then you have to annotate it. But
interestingly, though, it goes through a process of auto-generalization, that if it can't figure something out, it tries to make it as a generic.
Right.
And so sometimes it'll be constrained to object, but a lot of times you'll see things that this is a function of tick A goes to tick B.
Right.
And so that's the auto-generalization. So it tries to get things that if it's like an add, it may infer it as an int, or it may try to take it to something where it knows that there's a generic overload or something, and so it'll auto-generalize things. Otherwise, then it gets into a point of, I have no idea what it is, you need to tell me. A lot of times that'll crop up, like you want to invoke a method on something, like you're passing a string and you want to call substring or something like that. The compiler doesn't know that, so you have to tell it, oh, this particular parameter is a string. Once you've done that, it knows it's a string and you can access the methods on there. All right. This is going to customize the language. So one of the common tasks that we all have to do, string building, right? It's not complicated, but it would be really cool if it was part of the language. So in this example, let me open system text because I'm going to use the string builder for this. But now I'm going to define this type. So computation expression is going to compute the value of a type. This particular computation expression is based on the type called string fragment, which has 3 value types. It has an empty, it has a fragment which contains a string, and then it has concat, which contains the tuple of 2 string fragments, right? And here's an example of how you can extend a discriminated union. I just decided rather than going through a separate module, I would override the toString on my discriminated union. And so it'll match recursively. This is how it's going to end up computing that final string. It recursively goes across, walks the string fragment tree, and uses a string builder to combine all of these strings into one. But in my code, let me invoke that before I forget. In order to activate the language extension, I need to define my builder class. And I'm going to do that. I'm going to call it type string fragment builder. And you can see it's got a 0. So this is essentially an empty on a struct or something like this. This is the base value for it. In this case, I just want empty, which is, notice here at empty, I'm sorry, I'm struggling to see my cursor from this distance. There we go. Now, you see empty, I'm not referring to empty as part of string fragment. The compiler is figuring that part out for me. It knows that there's an empty on the string fragment. Now, and so these methods are responsible for these are the ones that will handle when the compiler desugars the computation expression later. These are the method chains that it'll go through. So here I will run this. I'm going to create my type, and you can see it's done that below. And I need an instance of it. So let build string get new string fragment builder. Also notice that I don't have to use new. F# doesn't require that, and it only suggests that you use it if it's idisposable. And it uses that more as a guideline to say, hey, this thing is something you might want to dispose. It doesn't actively enforce that. So I'm going to create that instance. And a fun string to build would be the lyrics to the song Bingo. So here's a module, and it's got a private function called build name phrase, and it accepts a full name. And now we see build string. I'm not referring to a string builder in here. I just have build string, and I'm yielding several strings. Similarly, in the build clap and spell phrases, we're building a string, and we have a for loop inside of build string, and we're going to just yield a few more pieces. And to build a verse, we'll just yield. And what this yield exclamation is doing is it's going to say, okay, the result of the function that I'm going to call is going to be another instance of this computation expression, so invoke that as well. So it'll go down the tree. You'll see that a lot in the asynchronous workflows. You'll see something like a return bang, and that's going to say invoke this thing, this sub asynchronous workflow as part of this. So you don't have to go through the extra hoops of doing that. And you'll just see yield a bunch of stuff. Let me create this module. And we just have the few numbers on there. Let name is bingo. We split out the letters, bingo. And now we can go build verse name, and we see all of the string builder done as a natural part of the language instead of having us manage all that stuff. Some other people have done things that are more interesting, like the Embrace framework is for offloading cloud-based computations. You can pass it an expression, and it will process that in the cloud and give you the result back. And so there's a lot of things that are being done with these. Let me switch back, sorry. As they stand, you can extend existing builder types. So if you find that there's a couple of places on query expressions, for instance, where they didn't implement a particular overload of one of the enumerable extension methods, you can go and provide that by using an extension method on that builder class, and then further customize the language and have custom operations inside of your own query expressions. So in summary, F#, powerful multi-paradigm language. It does play nicely with other CLR languages. If Brad wants to go into the Xamarin stuff, I don't know what time it is. Okay. It's a little different in the Xamarin world because it's really a translation into a different language for that. But as far as Mono and .NET goes, it plays very nicely with the other CLR languages. The constructs are intended, particularly record types, tuples, discriminated unions, those are intended to keep you focused on the problem instead of all of the plumbing that you have to do in the other languages. Things like like F# Interactive really let you explore the problem to make sure you're coming up with the right solution, and you know that it works, you know the code, you've already written the code, you can adopt it and integrate it into your projects easily. And there's the tagline. So, John Carmack, pretty popular guy, particularly mid-90s and beyond. No matter what language you work in, programming in a functional style provides benefits. You should do it whenever it is convenient, and you should think hard about the decision when it isn't convenient. My programming style, even in C#, has definitely taken on a very functional flair, but it doesn't go far enough. It doesn't give you things like curried functions, and I doubt it ever will. There's just too much legacy with it. They could probably do something aspect-oriented, but the convenience of pipelining and function composition and higher order functions in particular, as evidenced through the popularity of LINQ, really drive home what functional programming can do and how it can improve your code, how it can drive you to a better solution in less time. So if you'd like to know more, I've got a book which we'll give away a copy of. F# Software Foundation has tons and tons and tons of information. Try F# is a good place to try it in your browser if you don't have Visual Studio handy. I think there's another site that I can't think of. I lost. And then there's the F# language reference on MSDN. I have all of those links on my blog as well. So thank you very much.